So now that we've gotten a nice overview of the solar system and its various properties, it's time to get started to look in more detail and get a deeper understanding of what has taken place. To do that, we're going to start out by considering how the solar system got here. In other words, how did it form? Well, clearly we can't go back in time to watch, but there are some interesting clues that are available to us if we are careful observers. We can look carefully at the solar system's properties today, and by these use some simple physical laws and get a very good idea of what must have taken place long ago. Let's start out, for example, with the motions of bodies in the solar system. Consider for a moment that all the large planets in the solar system all orbit the sun in the same direction. When you consider also that they orbit the sun in a flat plane, this becomes a significant observation. They're not just all randomly going at different directions and different inclinations, but there's some order here. Finally, consider that the planets rotate in the same direction on their axis with just one or two exceptions. So we begin to see a pattern here to the motions of the large bodies. When you add to that the fact that the moons of the solar system, not only ours, but those of the outer Jovian planets, also orbit around their planets in the same direction, orbit in a relatively flat plane, and yes, spin on their axis, all in the same direction, we again begin to see a pattern here in the motion of bodies in the solar system, and this is an important clue as to how they formed. Now let's consider one other aspect that's significant. You might remember in our last lecture we noticed that there were terrestrial rocky planets in the inner solar system, closer to the sun, and there were gaseous, icy Jovian planets in the outer system, farther from the sun. This too is an important clue for us to understand the formation of the solar system. When you consider those compositions, it begins to make sense, doesn't it? The fact that we would see only rocky material near the sun where it's warm, whereas farther from the sun where it's quite cold, we could have gaseous and even icy materials. Think, for example, again, the terrestrial worlds and even the smaller asteroids are rocky and are in the inner solar system. But the large Jovian planets, and yes, the smaller comets and Kuiper belt objects, are icy in the outer solar system. We begin to see a clear division here, two major areas of the solar system by composition. Well, even with just these few observations, and of course many more, scientists have been able to put together a theory to explain the formation of our solar system. This theory is known as the Nebular Theory. And basically it states that a huge, large cloud or nebula slowly formed our solar system. Again, these properties, as we'll see in a second, would result from a cloud like this existing in space. Now, when you consider that this cloud, of course, would be composed of many, many, many uncounted trillions and trillions of tiny little particles, each particle having a tiny bit of mass, they would all have a very slight attraction for each other, wouldn't they? And so over time, this cloud would slowly begin to contract. And as it contracted, it would eventually form our solar system. Now, of course, over time, most of the matter in the solar system would end up in the center as our sun, and we certainly see that. Well over 99.99% of all the matter in the solar system is in the sun. But what about the planets and other objects? Well, the point is that these would form as smaller concentrations outside of the sun. Now, first of all, it's quite interesting that as we look out far into space where we think new solar systems are forming, we actually can see exactly this process. We don't see it occur quickly in our lifetimes, but we do see different stars at different stages of forming a solar system. In fact, one of our diagrams here shows quite a number of these disks of material surrounding young stars. We've even been able to find a few where we can kind of zoom in and get a closer look, a closer picture at these clouds of material around young stars. And this, of course, gives us confidence that our idea is correct. But the question is, how'd they get like that? Why is it that as the cloud's contracting, we notice these objects begin to flatten? Well, this goes back to what we outlined at the beginning, some simple basic physical laws. Laws of angular momentum and gravity and so forth dictate that the cloud must assume a certain particular shape, and certain things must happen to this cloud. Let's take a look at each one of these. Number one, as the cloud contracts, it's going to heat up. Why do we say that? Well, think of this. As the particles get slightly closer together, their attraction grows slightly, and therefore their velocity or speed grows slightly. And as particles move faster in a gas, you and I would call that a higher temperature. And so as the particles are streaming towards the center, increasing their speed, the temperature is growing in the center. The cloud is beginning to heat up. The second thing our cloud does as it contracts is it begins to spin faster. And again, some of you may be familiar with the concept of angular momentum. Well, as our cloud is contracting, there is a slight outward centrifugal force as the cloud begins to spin that is going to cause it to flatten. Now, this would be a subtle effect at first, but over time this effect would grow. And so again, the rotation speed of the cloud slowly increases and it begins to spin faster. What again is going to be the result of that spinning, and again that very slight outward centrifugal force? Well, that force is going to act perpendicular to the axis of rotation. So material above and below this flattened plane could easily fall downward, but material, again perpendicular, could not. And as a result, number three, our cloud is going to flatten. The spinning cloud flattens. So these simple physical concepts explain to us that a roughly spherical cloud would eventually, again, heat up in the center, begin to spin faster, and flatten into a disk. And that's exactly what we see when we look out at other solar systems that are forming. So we've made a good start, but let's consider then our second major observation we mentioned earlier, and that is, why do we have, again, the rocky inner solar system and the gaseous or icy outer solar system? Well, as we mentioned, simply put, the inner parts of the disk are going to be hotter. That's where the particles are going to move the fastest. And as a result, as these particles start to stick together, any gaseous icy particles are eventually going to be vaporized by the heat of our young sun. And so as a result, rocky planets, rocky objects form inside a certain distance from the sun. Gaseous icy particles predominate outside that distance. That particular distance is called the frost line. Okay. Now that may vary in each particular solar system somewhat, but the point is there will be a distance at which it is too warm for icy, gassy material to survive any longer, and you simply would have very little, if any, of it there. Rather, inside that distance, you're going to end up with rocky bodies, whether large or small. Outside that distance, though, it would be cold enough for the gas and ice to survive, and as a result, you could easily build planets of gas and ice. So we see in our diagram here again, the frost line. This is that distance from the young sun, kind of a demarcation, so to speak, where you get either rocky bodies or gaseous icy bodies. So how do we envision the planets actually forming then? We've got this flattened disk. It's made up of numerous particles. Well, once again, over time, we're going to slowly lose those gaseous icy particles inside that frost line. But these rocky metal particles are going to start to stick together. And as they stick together, they get a little bigger and a little bigger and a little bigger, and they began to form what we term a planetesimal. A planetesimal is much larger than a particle, but it's much, much smaller than a planet. Well, as these planetesimals grow to so many hundreds of feet, perhaps several miles, tens of miles in size, they begin to acquire a bit of gravity and are able now to pull in more particles and grow even bigger and bigger and bigger. Eventually, these planetesimals can become significantly sized. Over time, the planetesimals may encounter each other, stick together, and eventually begin to form our larger planets. So while this is a very simplified explanation, it does give you a pretty good idea of how this process would have occurred. Now, of course, as these planetesimals each grow larger and larger, and they begin slamming into each other, our planets again get larger and larger. And as our young planets essentially have the remaining planetesimals strike them, this is really the final stage of the formation of planets. Large planetesimals bombarding these young planets. What do we end up really seeing there? Well, we end up seeing huge craters left on the planets. So really we would expect all of the planets to have started out with a heavily cratered surface. Now a few of those planets, for example Mercury and even our moon, have not changed their surface at all since that very beginning, since that formation. And as a result, we can still, to some extent, see the original cratered regions of those planets due to that late stage of formation, the final planetesimals really striking those bodies. Well, that gives us a pretty good idea of how the terrestrial planets formed. Let's move on now and discuss how the Jovian planets formed. We mentioned a few minutes ago that, of course, outside that frost line, we're going to have gas and ice in large abundance. And, of course, at a greater distance from the sun, we have a greatly increased volume of material. And therefore, there's a tremendous amount of this material with which to form planets. And so out here we have many more planetesimals forming. And as they stick together, clearly we're going to be able to build much larger planets, aren't we? And as those planets, of course, get larger, their increased gravity is going to draw in even more of the remaining material. We're going to end up with some very large gaseous planets outside the frost line. So why is it that the Jovian planets have such large moons? We don't really see that around the terrestrial worlds, Mercury, Venus, and Mars. Yes, Earth has a large moon. That seems to have been somewhat of a special case. We think likely that Earth suffered one final large impact that broke some matter free, which then formed our large moon. But as a rule, the terrestrial planets simply didn't have enough material with which to form large moons. Why is it the Jovian planets did? Well, the answer again really is that there was so much more material in the outer solar system. And as these large Jovian gas planets are forming, they become so large that they actually begin to form miniature or smaller disks of material around them. And within these disks, we can get a similar process occurring. Particles stick together. They form planetesimals. Those planetesimals now can form fairly large moons, somewhat larger than our moon. So again, a simplified explanation, but it does provide us a good starting point as to the formation of the Jovian moons. What about the smaller objects in the solar system, the rocky asteroids, the icy comets, and even the Kuiper Belt objects? Well, if you consider for a moment their composition, I think you see how they fit in, don't they? Here within the frost line, we have planetesimals forming planets, but not all planetesimals ended up forming planets. Quite a few never quite did. Fundamentally, the reason for that, we think, is primarily the tremendous gravity of Jupiter, tending to influence some of the remaining rocky planetesimals and preventing them from forming a large planet. Well, what's the result? We still have some rocky planetesimals in the inner solar system. Today, you and I would call those asteroids, relatively small rocky bodies, relatively unchanged since the beginning of the solar system. A similar argument would apply to the icy comets and even the Kuiper Belt objects. Here in the outer reaches of the solar system, once again, for various reasons, primarily the tremendous space between these objects now at great distances, collisions would be fewer, wouldn't they? And we might end up with some planetesimals growing to a certain size, but no bigger. And as a result, today we see numerous small comets and, so to speak, medium-sized Kuiper Belt objects. So these are really leftover planetesimals. And as a result, they're very interesting to planetary scientists to examine. What can we learn from them? Clearly, some of them have really not changed much at all. And as a result, they're valuable to us because we can examine them and learn about what conditions were like, what objects were like early in the solar system. On the other hand, perhaps some of them have interacted somewhat, and we might get an idea about those interactions and learn what types of things occurred to alter these objects. So even the smaller objects of the solar system are quite valuable to us to study. Well, we have one other big question we'd like to address. When did this occur? When did all this happen? How could we get an idea of how old is the solar system? Well, it comes back to some simple concepts, some simple processes that we borrow from geology. And that is, geologists are quite good at telling us the age of a rock based on its composition. We determine the age of rocks by analyzing them. And why is that? Well, rocks may form with a certain amount of different elements. Some of those elements are going to slowly, gradually change into other elements. And geologists can measure the rate at which that occurs. And as a result, if the rate tells us that perhaps element A changes to element B at such a rate that half of it changes in, let's just say, 1 billion years, well, to put it simply, if we were to find a rock with half of A and half of B, we might say this rock is 1 billion years old. Very simplified example, but I think you see the point. We call this process radiometric dating. It's a very valuable, very powerful tool to give us the ages of rocks. Well, clearly we can't go out and necessarily tell you the age of a planet, especially if we don't get our hands on it. But if we can get our hands on some of the rocks, we could, couldn't we? Now again, we have very limited samples of other planets. Obviously we have Earth. Our astronauts have brought back samples from our moon. We actually believe we have a few samples from Mars that have found their way here after maybe being blasted off the surface. But the point is, what's the oldest rocks we can possibly find? Here on Earth, rocks are subject to many processes that may weather them, change them, erode them, alter them. The oldest rocks we've found on Earth are approximately 4 billion years old. However, the rocks from our moon that the astronauts have brought back are slightly older, 4.4 billion years old. And we have one final source of material that's very, very useful and important for us, and that is meteorites. We're going to talk about these a little bit later briefly, but for now, imagine small pieces perhaps of an asteroid over long periods coming closer to Earth, and a few of these are going to fall to Earth, and while many of them may burn up on the way down, some of them will reach the ground. And we call these objects meteorites. We said earlier that some of those may be from asteroids that have not hardly changed at all. So these are extremely valuable for scientists to be able to pick up, analyze, and get a date for. What have we found there? Well, the oldest meteorites are approximately 4.5 billion years old. So given a short amount of time for the rocks to actually form, we now believe the solar system to be approximately 4.6 billion years old. That's a remarkable piece of information, isn't it? 4,600 million years ago, our solar system formed. An amazing story for us to consider. So in this lecture, we've had a nice chance to step back and get a first look at how the solar system formed. Let's go ahead and do a review of some of our key concepts here. Number one, we looked at the motions in the solar system, didn't we? And based upon those, we began to come up with an early hypothesis on what might have occurred. Well, scientists have developed the Nebular Theory, which explains how a large cloud or nebula slowly contracted. Gravity would cause the nebula to contract, and as it would do so, it would 1. Heat up, 2. Spin faster, and 3. Flatten into a disk. We even saw some pictures showing this occurring around other stars, so we're quite confident that this did actually take place. We also then saw how at a certain distance from our young sun it would have been too warm for icy or gassy material to survive, and as a result we would be left with strictly rocky or metal type material inside this frost line. Here now these particles stick together. They formed what we called planetesimals, and over time these planetesimals would slam together and gradually build larger terrestrial planets. Outside the frost line, of course, we saw that the temperature was colder. Not only could rock and metal survive, but gas and ice could, and in much larger amounts. And as a result, as these particles stuck together, formed icy planetesimals, these planetesimals were much more numerous and eventually could build much more larger planets. So this gives us a very nice explanation, number 1, for the motion that we saw on the planets, and number 2, for the differing types of objects we saw, rocky versus gaseous. Finally, we finished up with a few minutes discussion on the age of the solar system. How do we know that? Well, again, fundamentally it comes back to analyzing rocks. What are the oldest rocks we can get our hands on? There's some quite old ones here on Earth, but by examining not only moon rocks, but meteorites in particular, we saw that this method of radiometric dating tells us the solar system formed about 4.6 billion years ago. So I think you can see how some basic simple observations can get us started with a deeper understanding of the solar system. From there we can continue to add more observations. We can update our understanding as we move along and come to a pretty good idea how the solar system got here as it is. So in our upcoming lectures, we look forward to getting into much more detail about the terrestrial worlds, the Jovian worlds, and other objects in the solar system.